So the photoelectric effect, right? So the photoelectric effect is a really interesting part of science, right? Because um, light has what we call a dual nature, right? What does it mean by a dual nature? A dual nature means light can act as both a particle, but it can also act like a wave, right? So if you look at a photon, we call it the wave particle duality. What tells us about the wave nature of light is the fact that light's got a frequency, it's got a wavelength, it's got wave speed, it diffracts and it reflects, just like what waves do, right? Waves have all of those properties. But then particles also have these properties, like photons collide with electrons and it transfers its energy, right? Photons act like quantized individual particles at times as well. So this wave particle duality gives light this really awesome property of a lot of things. Then we can go look at the wave equation, right, of light. So we've got E is equal to HF, where now E is the energy of the photon, H is Planck's constant, and F is the frequency of that light, right? And then we can also then look at the wave equation in terms of the velocity, the frequency of the wavelength, where V is equal to F lambda, where F is the frequency of the light, lambda is the wavelength of that light, and V is going to be the speed. But in this case, because we're dealing with light, not just any random wave, then we're going to know that the speed of that wave is going to be equal to the speed of light, c, 3 times 10 to the power of 8. It's the universal speed limit. Nothing can travel faster than the speed of light in a vacuum, right? So then we eventually have c is equal to f lambda, where we need to note that f is inversely proportional to lambda, right? The greater your frequency, the smaller your wavelength, or the greater your wavelength, the smaller your frequency. Very, very important when we're looking at that there. Then let's look at the photoelectric effect itself, right? So what is the photoelectric effect? So the photoelectric effect states that electrons can be ejected from a metal when a light of a sufficient frequency is incident on that surface. So what we can see is that you'll have a photon, that photon goes, it'll hit that metal. And if that photon has got enough energy, that photon will have that metal eject what we call a photoelectron, right? So we will eject an electron in exchange for the energy that that photon gave us, right? So again, what do we mean by light? Light, we're talking about electromagnetic radiation, right? Of any kind. Sufficient energy means it's got to have high enough or more than some value. What is that value? We'll get down to figuring out what that value is. And again, when you talk about being incident on, it means if it shines on. If that photon shines on a metal, that will then eject it, right? And, you know, there's a place where this happens every day. And especially if you live in South Africa like us, you probably need one of these things in your house, which is like a solar panel. And a solar panel uses this very technology, right? Where it uses light to eject electrons. Those electrons do what? They carry a current, and you now have electricity simply by utilizing light. Okay, so very important here that F must be greater than FO. What does that mean? It means the frequency of that incident light, the frequency of whatever light it is, must be greater than the threshold frequency. What is our threshold frequency? The threshold frequency is the property of a metal or a group of metals, which is basically the minimum amount of the minimum frequency of light required for me to liberate an electron or for me to eject an electron, right? And we can connect that threshold frequency, that FO, with what we call WO. WO is our work function. We connect them using the following equation. WO, our work function, equals H, Planck's constant, times the threshold frequency. And our work function is going to be what? It's going to be the minimum energy that the electron needs to be ejected from the metal. And if E, the energy of the photon, exceeds my work function, the photoelectric effect takes place, right? So think of it this, we used to like to make an example about the following. If any of you have ever been to like a gold reef city or you've been to any kind of theme park where they've got rides or anything else that happens there, right? Or any kind of place where there's an entrance fee and then there's activities to go inside, right? When you look at the equation of the photoelectric effect, we break those things down a number of ways. So the energy that a photon possesses, that E, can be broken down into two components: work function plus EK max. Let's see what that means. So if you go to, let's say you go on a date, or you go with your friends out to the movies, or to Randy's the show, or like the whatever kind of theme park show, where there's going to be an entrance fee, or a market where there's an entrance fee. So E, this is the total amount of money you've got to begin with, right? The money that your parents gave you for pocket money, that's the money you go there with. That money is going to cover two things. The first thing is going to cover your entrance fee. Without that entrance fee, you can't even begin to have any kind of fun. You will not be allowed into the experience. And the same thing happens with the photoelectric effect. Without meeting the minimum requirements of my work function, no electrons are going to get emitted in the first place. Any energy that's left over is the kinetic energy of the photon. So once you've paid for your entrance fee, this work function, the money you've got left determines the speed of your electrons. People who've got lots of money in their pockets have lots of money after paying your entrance fee. You've got lots of money left over. You're going to be running around like a headless chicken because you've got so much money and you want to spend it on all the activities. But if you went in and let's say you were given 50 Rand and the entrance fee was 49 Rand and you've got 1 Rand left, you're not going to be walking very fast. You're going to be walking slowly because you want to make sure you maximize your 1 Rand that's left, right? And sometimes it happens where an electron has just enough, or a photon has got just enough energy to only match the work function, where E is equal to WO. And there's no more energy for that electron that's going to be emitted to have any velocity. And all you basically do is have enough money to just join the party. Nothing else. You can't run around and go buy chocolates or buy sweets or buy a drink. So then you have zero kinetic energy. So this is important to break this equation down this way, because some questions will come and they'll ask you about what is the maximum speed of the photoelectrons. Photoelectrons being what? The electrons emitted by the photoelectric effect, right? So when you do the calculation, the initial energy we get from this equation here, E is equal to HF. You'll usually be given a frequency or you'll be given a wavelength, and you can use that to calculate E. The work function part, you're going to use that very same threshold frequency, right? Or you'll be given a work function and you'll use that to be able to calculate that. And then kinetic energy, a lot of the times they'll ask you about the velocity of the electron, or if this is the speed of the electron, what was the energy that the light possessed in the first place. So these are very important things that we need to then keep in mind. Remember what we said, the criteria for photoelectric effect: your frequency must be greater than your threshold frequency. The energy of your photon must be greater than your work function, or your wavelength of the light must be, in this case, sorry about that, it's not greater, but it's going to be smaller than your, if there's a threshold wavelength, that's going to be important there. And then the effect of intensity versus frequency, right? So intensity versus frequency. Intensity equals the number of photons that are incident per unit time. So think about intensity. When your light is brighter, your light is more intense, right? So that just means you're having more photons reach you with the same amount of energy. The energy amount doesn't change, right? So an increase in intensity equals an increase in photons, not energy, but photons. An increase in the number of photons equals an increase in the number of electrons that are emitted. So more photons, more electrons get emitted if you meet the minimum requirements, right? However, the electrons will be ejected with the same maximum kinetic energy. An increase in intensity will only result in an increase in current, right? More photons per unit time, not the speed of those particular things there. Then frequency, directly proportional to the energy of the photon. An increase in frequency is going to equal more energy per photon. Each electron released with greater maximum kinetic energy, but the same number of photons will be released. Therefore, no change in intensity. The current will be maintained. So increase in intensity will increase my current. Increase in frequency doesn't increase my current. It just increases the maximum kinetic energy that goes out there. And then finally, we have our what we call our emission and absorption spectra. And our emission and absorption spectra, again, remember, electrons orbit the nucleus of an atom in specific energy levels, right? So with emission and absorption spectra, an emission spectra, now, when you look at this fact, electrons can emit energy in the form of photons by moving from a higher to a lower energy level. So if you look at your energy levels, thinking back to early chemistry, your different orbitals and energy levels, if an electron moves from a high energy level to a lower energy level, right, it has to emit energy out of the system. That energy that's going to be emitted is going to be emitted in the form of light energy, right? And that light energy will have a very specific amount of energy. And that energy and that frequency is going to then be depicted by a specific color. And that's when you see those emission spectra with those various colors. And then absorption spectra, basically when electrons move up an energy level, they require energy. So they usually will absorb that energy from somewhere externally. And then electrons can absorb certain frequencies of photons by moving from a lower energy to a higher energy. So in a cool gas, there's certain absorbed frequencies. And then basically the energy you need to put in is the energy required to go from one energy level right up to the next energy level there. You'll see some of those questions as we go on. All right, we've got 40 minutes left. I want to try and just use 30 minutes to do the past paper question and then leave some time for you guys to ask us any questions. All right, for anyone that's just joined us on TikTok or on Zoom, please remember to follow us. We really appreciate it. Share the live with anyone who wants to come and join and benefit from this particular topic. And yeah, guys, watch our YouTube channel. We've got lots of videos that will help you guys in preparation for your prelim exams. Sweet. Let's look at question 10, right? So question 10 says, in a photoelectric investigation, light of different frequencies was radiated on each of two metals, metal A and B. The graph of maximum kinetic energy of the ejected electrons from metal A and the frequency of the incident photons is shown. So we can see here we've got maximum kinetic energy of the electrons and then the frequency of said light, right? In that case there. Then it says write down the numerical value of the gradient of the graph. We need to write down the numerical value of the gradient of the graph. What I want you guys to do now is post in the chat, what does the gradient of that graph represent before the numerical value? If you know the numerical value, fantastic, put it in there. But for now, tell me what quantity does it represent, the gradient of this graph? I'm going to give you guys 2 minutes to think about this one. Lurks come there on TikTok. Thank you so much for your answer. Really appreciate it. Rafido on Zoom, thanks so much for your answer there. Appreciate it, right? We're dealing with Planck's constant, right? Thanks for the answers that are still coming in now. Planck's constant is very important. So what is the numerical value of Planck's constant? If you can write down in the chat before I'm done writing here, you get bonus point. Sorry. There's our numerical value, right? It's going to be 6,63 times 10 to the power of negative 34. Thanks, Rafida. Thanks, Kitumetse there as well for putting that one in the chat. Really appreciate it. Let's look at 10.2. 10.2 says define the term work function. We did that one together, right? Where we looked at work function. And the work function is simply going to be the minimum energy needed for a photoelectron to eject an electron off of a metal's surface. Very, very important. Let's quickly put that one down there. So here's our answer. So I'm just trying to move this into the right place so you can see it. the minimum energy needed to eject an electron from a metal surface. That is the work function. Then it says 10.3, calculate the work function of metal A, right? How do we calculate the work function? The work function, we're going to use one of the equations we saw above. Let's quickly squeeze there. There's the work function. We can use this one here or that one there, depending on what information we have, whether we've got threshold frequency or we've got any other detail about it. So let's quickly go back. So one of the key things we can see here, right? If you look at your graph, the frequency down here, anything below this level here, I don't have any kinetic energy. So which means it's only at this point that I then have enough energy to even start producing kinetic energy. So this is going to then be a very important part. That becomes our threshold frequency. 5 times 10 to the power 14 hertz is our threshold frequency. We can then go work out what our work function is, right? So let's quickly go do that. So our work function, we're going to use that equation we just saw below. W naught is equal to H times F naught, right? H is Planck's constant. We already put that answer up there. 6,63 times 10 to the negative 34 times our threshold frequency we saw was 5 times 10 to the 14 hertz. That's 5 times 10 to the 14 hertz. If you plug that into your calculator, you should get an answer of 3,32 times 10 to the power of negative 19. And again, work function is a form of work. Work is measured in joules. So don't forget your SI units there, joules, right? That's how we work out our work function for metal A, given the information that we had above there. So just to quickly repeat, to get our work function, we're going to use the equation W naught is equal to H times F naught. How do we find F naught, which is our threshold frequency? We look at our graph. So on our graph, we can see that all of these frequencies of light here generate or they eject electrons with a certain amount of kinetic energy, but nothing less than 5 will give me kinetic energy. So 5 must be my threshold frequency. And then I'm going to come back and plug that into my calculation, and then I get an answer of 3.32 times 10 to the power of negative 19. Awesome. Let's do 10.3.2. They want us to find the value of X shown on the graph. Let's quickly go back at our graph and see what is that value of X. So the value of X is this one here. It says, what is the maximum kinetic energy when the frequency of my light is 12,54 times 10 to the power of 14? Well, we can then go work that one out a number of ways, right? Once we worked out either graphically or we can work that out using an equation, right? There's 2 ways. So I'll even show it to you in both ways, right? For this particular calculation. The first way I'll do it is say, well, I can actually use the gradient of the graph. And then I know I've got a point here. I've got a point here. I'm going to use, sorry, let me do this. I'm going to use this point and that point. Given the gradient of my graph, I know that this point down here is going to have X value 5, Y value 0. And then this point here is going to have X value 12,54 times 10 to the 14, Y value X. And we worked out, they said, what is the gradient? The gradient is going to be given as Planck's constant, this thing here. And I can use gradient formula to find that value of X. That's one way of doing it. And then another way of doing it is simply just using the formula. So let's start with the gradient method, and then we can do another method as well and show you guys both of them. Let me just move this up to create a bit more space for myself. So value of X in the graph, I'm going to use the gradient method. So we know that my gradient, M is equal to change in Y over change in X. Let's quickly have a look at that. So our change in Y, our gradient we were given as Planck's constant, 6,63 times 10 to the power of negative 34. Our change in Y, it's Y final minus Y initial. Our Y final is going to be this X value here of X, our y initial is going to be the y value of the initial point here, which is going to just be 0, right? So I know that change in y is going to be x minus 0. And then my x minus x2 minus x1, it's going to be this 12.54 minus my 5, right? 12.54 minus my 5, and that will basically work. Keep in mind, they're both times 10 to the power of 14. So then I'll quickly plug that in there. I'll have 12.54 times 10 to the power of 14 minus 5 times 10 to the power of 14. And then if you put that in your calculator and you solve for x, you should find an answer of, let me quickly just plug it in my calculator. Give me 2 seconds. It's going to be the bottom bracket times Planck's constant. Then you'll get an answer of 5 times 10 to the negative 19, right? For that one then. That's the value of x. If I use my graphical method, another way I can do this problem is if I use the equation, right? And if I use the equation, let's look at what information we've got and then how we can basically solve it. Remember, one thing I told you guys was energy. Let me just write it further up so I've got more space. Energy is equal to work function plus the EK max of my photon, right? And then if you use that, you can then basically try and solve for the maximum kinetic energy that we end up dealing with in that particular case there. So if I do that, I need to find each of the values. So when I use this, E is equal to, I'm going to have, I don't know what the energy of the photon was, but I know that energy is equal to HF, right? My work function is going to be equal to H times F naught plus my maximum kinetic energy, which is really what I'm trying to solve, right? So I'm going to just leave this as EK max. Do I have H? Yes, I've got H. It's Planck's constant. Do I have the frequency of the light I'm looking for? Yes, because I'm looking for this X here, right? The corresponding frequency is this 12,54. So I do have that, right? That 12,54. I've got that. Do I have my threshold frequency? Yes, I've got that too, because we said our threshold frequency is going to exist at this point here, 5 times 10 to the power of 14. And if I can plug all those values in, I'll then be able to solve for my problem. And if you take all of those and plug them into your calculation, you'll find that you will get the exact same answer. All right, Theo, do we have any questions on Zoom there? I'm going to just double check TikTok as well, because I haven't been looking at the chat before I know to carry on.
There's nothing in it.
Nothing there. Okay, fantastic. Thank you so much, Theo. Let me then pick it up again. Okay, so for us to continue, let me quickly go then to the next question. Okay, 10.4. 10.4 asks the following. How will each of the following be affected if light of frequency 12.54 times 10 to the 14 hertz, but higher intensity is used, right? How will each of these increase? So 12.54, right, is the light we were using at this point, right? That's the light we're using at that point there. So what will happen if I use light of the same frequency, but higher intensity? So this is the thing we need to note that we're answering. If I use light of higher intensity, what will the effect be on the following? The value of X. So the value of X, meaning the energy of my photoelectrons. Will it increase, decrease, or have no effect? I'm giving you guys 30 seconds to put that down. If I increase the intensity of my light, what will happen to the value of X, right? Which is the energy of my photoelectrons. 30 seconds, post your answers in the chat. If you've joined us recently on TikTok, we're going to have these interactive questions. I want you guys to post the answer that you think is correct, right? Thank you, Lurks there. Thank you, Sane, for your answer. Thank you, Unalina. Thanks, Kitumetse, for your answer. I'm going to give everyone else still 15 more seconds. to put your answers in there. Okay, don't be shy, guys. Remember, engaging and interacting, that's really how you make sure that you guys get your learning in there, right? Okay. Thanks, Mkuleko, for that one there. Thanks, Nani, for your answer. 5 more seconds for those that haven't answered. 4, 3, 2, 1. You guys are doing brilliantly today, right? And everyone got the correct answer. There will be no effect. Well, not everyone. The people that answered got the correct answer. The people that didn't answer got 0. And it's important, guys. Questions like this in a final paper, don't leave it blank. Rather, if you're not sure, rather guess. But before guessing, join our lessons. We'll help you know the right answer, and then you'll get the correct answer. But if you failed to find the right answer, at least guess, especially when they give you options, right? So for that first one, we're going to have no effect. Remember again, because intensity means I've got more photons. More photons means I'll have more photoelectrons, but they're all at the same energy. The only way to increase the energy of the photo electrons and the energy of, the energy of the photoelectrons is by increasing the frequency of light. Okay, now 10.4.2. How does increasing the intensity of the light affect the number of photoelectrons emitted per unit time? Now write down increase, decrease, or no effect. If you didn't answer the first time, this is your chance to make sure you are in the game. So make sure you guys put your answers down. So 10.4.2, the number of photoelectrons emitted per unit time. How will those be affected by me using light of a higher intensity? Thank you for everyone that's throwing their answers in there. Really appreciate it. Seeing some new names, which is fantastic. New names are always good. It means people are getting engaged and getting involved. I'm going to give you guys 10 more seconds. Thanks, Danyiko. Thanks, Mpiwe. Thanks, Bongo, guys. Your answers there. Precious and Godfrey Wakile. That's brilliant. Okay. 5. If you haven't answered, quickly put your answers in. 4, 3, 2, 1. All right. And then the answer for this one, drum roll, is everyone that has answered got it correctly. And everyone that didn't answer got 0 again. It's going to be increase. Right? As I've just mentioned, if I increase my brightness, I increase the number of photons, and I increase the number of photoelectrons emitted if the photoelectric effect does take place. But it doesn't affect the energy of my photons. It doesn't affect the energy of my photoelectrons. All right. And then the last question quickly. Metal B has a larger work function than metal A. So remember, metal A is the one we've been dealing with the whole time. That's this function, this graph over here. So this metal B has a larger work function than metal A. Redraw the graph above in your answer book. Do not include values on the axes. Label this graph as graph A. And then it says on the same set of axes, sketch the graph for metal B. Label this graph as B. So what I'm going to do, I'm going to just copy this on my side, and then I'm going to paste it down there. Then we can redraw it on there. If you want, in the meantime, you can quickly tell me in writing in the chat, how will the graph of B be different to the graph of A, while I copy this and paste it at the bottom for me to give you guys the correct answer. Quickly post in the chat, how will the graph of B be different to the graph of A? Just want to crop this. Okay, it's not cropping, but I'll just put it down there and I'll just redraw it. Okay. Prelim has given an answer there. Tenyuko's given an answer there. Well done, guys. You guys are giving the right answers there. So one will say, it'll have a higher frequency than graph of A. I get what you're saying, and then I prefer Tenyuko's answer. It'll move to the right, right? And then Lurks will say it'll have a higher threshold frequency than A. So basically how it will look, let me just bring my ruler in there so we can draw it in the right way. They didn't say how much, but it doesn't really matter. I'm going to draw this in purple, and it'll basically look like that. So my threshold frequency is going to be higher than that of A, and then I need to label it metal B, right? And that's what happens. Remember, what's very important there, your gradient must be the same, right? Because the gradient is going to be Planck's constant, and Planck's constant is constant for both functions. So the two functions, the two graphs must be parallel, very important. And then it must be to the right-hand side. So those are the 2 marks that you get for a question like this. Very, very important. And I hope that makes sense to everyone, guys. Thank you so much for all your answers. We've got lots of time for Q&A today because we did manage to then finish our questions a little bit earlier than planned. So you've got 20 minutes of Q&A. Any questions you guys would have for the last 2 topics we just did, the first one being electrodynamics, motors and generators. And the second topic we did was photons and electrons, aka photoelectric effect, optical phenomenon, right? Any questions you guys have on those 2 topics, I am here for the next 20 minutes to be able to answer those questions for you guys. Whatever your questions might be, you guys can shoot. I'll give you guys a minute or 2 to have a think about it. If you don't have questions, I'm going to just find another question for you guys to do. Then we can just have a look at that question together. Dinani says, what time do the classes start? The classes do start at 6 p.m. until 8 p.m. Mondays to Thursdays. Lurk says off topic. Are the lessons daily? Lurks, if that is your question, it's not off topic. It's very much on topic. Yes, Mondays to Thursdays is when we do the lives leading up to prelims, right? We're doing this series just to help everyone prepare for their prelim exams. Okay, I've got a message from Masiho on this side here that says, why is the gradient Planck's constant? Not a problem. That's a great question. Let's quickly have a look at it. So when we look at this, it's a graph of kinetic energy or energy versus frequency, right? So if we have a look at this here, if I've got a graph of E versus F, okay? Now, if I were to put a line, so here's a line, and I want to write down the equation for that line, right? So when I write down the equation for this line is going to be as follows. It's going to basically be my gradient is going to be change in E over change in F. But here, I'll basically have E is equal to something, my gradient, right? Let's call it X in this case here, or let's call it P. Or in this case, let me just call it what it is. Let me call it H as the gradient. And then F is my X-axis. Think about how I would have Y is equal to MX, right? Plus C in that case there. So Y is the same thing as my energy there. M is the same thing as my Planck's constant. And then X is the same thing as my frequency, because you can see my X-axis is F. Then you can tell, because of this little symmetry that we've got going on, that we are going to have that graph be the same thing as E is equal to HF. Then you know that your gradient is going to be Planck's constant. Masiho, I hope that helps for you. And then Sbongo says, please, can we do another question? We're more than welcome. Sbongo, which question do you want to do? Photoelectric effect or motors and generators? Because we did 2 topics today. I'll give you a second to quickly come back with that answer, and then I'll find a question in 2 minutes. Photoelectric effect, it is my pleasure, sir, for me to do that for you. Okay, give me 2 seconds and I'll quickly find a question, then we can do. Okay, lurkers that also like to do photoelectric effect, it's with pleasure that I will do that for you. Okay, let me quickly find one. Hold on 60 seconds, guys. If anyone has just joined, I'm just quickly looking for a new question for photoelectric effect. We just finished the question we were doing now, and then we'll do one more question. And then during our Q&A session, people said they wanted to do more questions on the topic. Okay, someone asked there, if they're practicing on their own and they've got a question, how can they reach us? So we, on our side as the learning space, we do have our own tuition programs. So if you are not part of our schools and a program that's happening at one of our Clo Institute schools, if you're not a part of the Clo Institute program and you're coming privately, the learning space, we've got our own center where we do lessons in person and lessons online, and you're more than welcome to book a session with one of our tutors. We've got varying packages. If you just go to our website, you'll be able to engage with us, thelearningspace.co.za, and you can go book a lesson with a tutor on our side. So if you guys are keen to get a tutor to help you, just go to thelearningspace.co.za. You can go and book it, and then there's certain fees that you'll engage with, but you can engage with our administrative team to help you find the right tutor for you, in person or online, depending. If you're based in Johannesburg, you can connect with us in person. If you're outside of Johannesburg, then what you guys can do is you can just connect with our admin team and they'll get you a tutor to help you online, one-on-one, in that kind of thing, or even in a small group setting. Okay. Other than that, if you're practicing by yourself and you need extra help and maybe you don't have money for a tutor, just go to our YouTube page, go to our TikTok page. We post lots of content where you can see us practicing certain things out there. Okay. Cool. I found a question for us to do. Let me quickly copy it onto my whiteboard and then we can get started. Okay, I'm going to paste this bit by bit. Just bear with me. Just so we've got space to write down our answers, right? Okay, it's 2 more questions. We're almost done. And then I'm pasting the last question now. And then we can do the question together. Okay, let's have a look at this question. It says question 10, it says, light is incident on the cathode of a photoelectric cell connected to a battery and a sensitive ammeter, as shown below. What conclusive evidence about the nature of light is provided by the photoelectric effect, right? Remember, I mentioned this thing at the beginning, that light has got 2 natures. It's got a particle-like nature and it's got a wave-like nature as well. The photoelectric effect tells us right now about light's particle nature. So the particle nature of light . That's what it is telling us, or the fact that light is quantized, right? But the particle nature of light is what the photoelectric effect tells us about. Then the next question says, the cathode has a work function of 3.42 times 10 to the power of negative 19 joules. Define the term work function. That one we did again earlier. I can just quickly copy and paste that from the previous one. But again, work function, for those that weren't with us earlier on, work function is the minimum energy required that can eject electrons from a metal surface. That is what a work function is. Let me quickly paste this here. Then we can just use this and move on. I'm going to move a bit swiftly so we can get to calculations before our time runs out. The session ends at 8 o'clock, right? So then it says light of frequency 5.96 times 10 to the power of 14 hertz is shone onto the cathode. Calculate the maximum kinetic energy of an electron ejected from the cathode. So let's try and make sure we have all the information we need. Here's a piece of information we're looking for, is the work function of this cathode, 3.42 times 10 to the power of 19. That's the work function. We need to find the maximum kinetic energy. So remember, how do we do the calculation? We've got energy is equal to the work function plus the max kinetic energy of our electrons. And then again, remember, E is equal to HF, and then we can take it from there. So we are given the frequency, so we can then know that since E is equal to HF, we can then say HF, right, is equal to work function was given to us in joules, so we'll leave it as work function plus EK max. Do we have everything we need? We've got our H, it's a constant. We've got our frequency, it was given up here. We've got the work function, it was given further up there. And we're going to calculate the EK max. Let's plug our values in and solve. So H is going to be Planck's constant. That is 6,63 times 10 to the power of negative 34. And then our frequency of light was given as 5,96 times 10 to the power of 14 hertz. That's going to be equal to our work function. Work function is given there up at the top, 3,42 times 10 to the negative 19. So we can do that there. That's 3,42 times 10 to the power of negative 19 plus our EK max. And then we can solve our EK max simply by taking our HF minusing our work function and find that there. So put that into your calculator and you can find your EK max is going to be your H times F minus your work function. And if you plug all of that in your calculator, you should get an answer of 5,3 times 10 to the power of negative 20 joules, right? Okay, hope you guys are happy there. I hope it makes sense in terms of how I got to that answer over there. And then we can move on to the next question. If you guys are happy, that makes sense, please just put a thumbs up in the chat or in the reactions for me to move to the next question. Theo, are you there? I heard someone speaking.
Yes, Ernest, it was me. I'm seeing they're saying your screen is not clear.
Is it also blurry on your side?
Yes, it was, but it's fine now.
Is it fine now? Okay. All right. So that's the, yeah, I've calculated then the maximum kinetic energy, very important. I use the equation energy is equal to work function plus max kinetic energy. I can work out my energy because it's HF and I've got that. The work function was given to us, W naught. And then we just solve for EK max, 5.3 times 10 to the power of negative 20 joules. 10.4. The ammeter registers a constant current of 0,012 amps, right? Coming out there. Calculate the minimum number of photons of light that strike the cathode in a 10-second period, right? So how do we go and work that out? Well, we need to go and work this out as follows. Someone just asked now, do you have a YouTube channel? Yes, we definitely do. If you're on TikTok, go to our page. There'll be a link to our YouTube. So just look for the Learning Space ZA. So it's youtube.com/the Learning Space ZA, but just go to our TikTok and there'll be a link straight to our YouTube there. Okay, so 10.4, the ammeter registers a constant current of 0.012 amps. Calculate the minimum number of photons of light that strike the cathode in a 10-second period, right? So I've got current. I need to figure out how many photons. So from the current, to figure out photons, I'm going to need to do the following thing. So I'm given current, my I. To get to photons, I need to first work out, well, how many electrons? How can I get to electrons? Current is a flow of charge. So I can go work out my charge, right? Once I know my charge overall, I can divide it by the charge of a single electron, and that will give me then the number of electrons individually. So I need to look at that process there. So let's first work out our charge, right? Where Q is equal to I times delta T, all right? The current we were given was 0.012. The time was a 10-second period, and then that's in the right SI unit. That's just going to be 10. So we should then have a charge of 0.12 coulombs, right? So 0.12 coulombs. I need to now find, that's the charge that has moved through. How many electrons is that? Well, let's take the total charge divided by the charge of one electron. That's very easy. So we know that the number of electrons is going to be the charge overall divided by the charge of one electron. Sometimes they write it as QE, like that, all right? So then we know the total charge we worked out to be 0.12. What is the charge of one electron? You'll find this number on your formula sheet, which is 1.6 times 10 to the power of -19. So if you take that there, 0.12, right, number of electrons, and you divide it by the charge of one electron, so the charge overall divided by the charge of one electron, you then should get an answer of 7.5 times 10 to the power of 17 electrons. I hope that makes sense to everyone. So they gave us the current. Remember, current is flow of charge, right? So what I need to do with the current is find how much charge was there in 10 seconds. Once I know how much charge went by, remember, charge is simply the collective charge of all the electrons. So I divide the total charge by the charge of one electron. That will give me the number of electrons that flowed in that time. So that's how you answer that particular question there. Then we can move to 10.5, which is our last question for the day as we wrap up. And 10.5 says the intensity of the incident light is now increased. How will this change affect the reading on the ammeter? Choose from increases, decreases, or remains the same. I want you guys to answer this final question because I now believe in you guys. You guys have managed to do this really well. Sunny is like ahead of the game. Sunny has already answered the question. Let's see how everyone else is doing. So the intensity of the light is now increased. How will this change the reading on the ammeter? Right, simply increases, decreases, or remains the same. Thanks, Peluso. Thanks, Rosina. Thanks, Denyuko. For those that have just joined on TikTok, there's our final question for the day. We've been dealing with a photovoltaic cell. We've now increased the intensity of the light. How will this change the reading on the ammeter, right? Increase, decrease, or remains the same. I'll give you guys 15 more seconds. You should know this one. As we've been doing this lesson, you guys have been doing very well. Thanks, Colin. Thanks, Ralebo. Thank you guys for posting that. Thanks, Bongo, for posting your answers. 10 more seconds, guys. For those that haven't posted the answers, remember, number one rule is never leave a question blank, especially if it's multiple choice. The worst you can do is guess. 5, put your guesses down if you're not sure. Put your answers down if you are sure. 3, 2, drum roll. Time is up. As we know, when we increase the intensity of the light, it increases the number of photons. When the number of photons increases, it'll increase the number of photoelectrons emitted. So the more electrons I've got per unit time, the more current I've got. Because remember, what is current? It's my flow of charge. So our answer there for this final question is going to be a big fat increase. Guys, thank you so much for your time today. I really appreciate it. This is me. I hope you guys found this lesson helpful. If you found it helpful, please, please, please give us a thumbs up. We really do appreciate it. And what you guys can do is join us again tomorrow. Tomorrow, we're going to have a mathematics lesson on one of the topics that people struggle with again. It is going to be probability and counting principles. I know people want to get help on probability and counting principles. So please make sure you join us tomorrow. Spongo says I must please repeat the reason. So for 10.5, we are increasing the intensity of the light. When I increase the intensity of the light, what does that do? It's going to liberate more electrons, right? So more photons equals more electrons. It doesn't change the energy, but it changes the number of electrons. But the number of electrons per second is still going to be more current, more charge per second. So my ammeter will then show an increased reading. Sponga, I hope that helps you again there. Guys, thank you so much. If you guys are not already following us on TikTok, please follow us on TikTok. We appreciate it. Go check out those videos. They will help you guys a whole lot. We cover a range of topics. When you're not here, go to our YouTube as well, the Learning Space ZA, on all social platforms. And you can get really awesome learning content from us. Other than that, we have another lesson tomorrow hosted by Tapang from 6 p.m. to 8 p.m. tomorrow, doing a maths lesson on counting principles and probability. So you don't want to miss that one. Very, very important. Make sure you guys all come together for that lesson, and we'll help you pick up that topic, because usually a lot of people struggle to teach that topic and learners struggle to grasp it, and we will make it really easy for you tomorrow. I do promise that. Okay, if you guys really appreciated the lesson, I appreciate you guys. If you feel like we gave you 5-star service, I would appreciate you giving us a 5-star review on Google. Just go to Google the Learning Space. And then when we come up, go to Google, give us a 5-star review. Feel like we gave you 5-star service. Really appreciate you guys. Thank you guys so much. Please have an awesome rest of your guys' day. We will see you guys tomorrow. I'll hang around for 2 minutes if there are any academic-based questions. But other than that, we're going to head off and we're going to sign off. It's been great. It's been awesome. Thank you very much for spending time with us, guys. See you tomorrow. Cheers.